Hello and welcome back. Today's video we are going to touch another property, that's energy, that we need in the study of fluid mechanics ahead. We'll study all that we need in the fluid mechanics about energy. So the topics that will be covered are energy and its forms and units as well. What are microscopic and macroscopic form of energies? Microscopic energy as latent and sensible forms. Then internal energy and enthalpy, specific heat, relation of internal energy and enthalpy with specific heats. Then enthalpy and internal energy of incompressible substances. So let us start. So we'll start with energy. So first of all, what is energy? And we know that ability to do work is called energy, and the rate at which this energy is being done is called power. So what is energy? Ability to do work. Now there are various forms of energies like thermal energy, mechanical energy, electrical energy, magnetic energy. There are different forms of energies, and law of conservation of energy states that energy cannot be created or destroyed, but it can be converted from one form to another form. With every conversion there will be losses. We call them energy conversion losses. That is why we define efficiencies at any conversion stage. So units. Now what are units of energy? The SI unit of energy is joule, and it's in English system the unit of energy used is BTU, British Thermal Unit, and 1 BTU is roughly equal to 1 kilojoule. It is roughly equal to 1 kilojoule, not exactly. And another unit that we use for this energy is calorie. 1 calorie is equal to approximately 4.2 joules. Approximately. And one more unit of energy is also calorie, capital CAL. This is small CAL, and this is what we call as food calorie. This is the calorie that we normally use in diets. Like we say this food has this amount of calories. That calorie 1 capital CAL, that calorie is equal to 1000 small CAL, this calorie. Or 1 food calorie is 1 kilocalorie. So when we say, for example, when we say peanuts, 100 gram peanuts have 550 calories. For example, when we say, it means 100 gram of peanuts will have 550 into 1000 calories of energy that we study in science, calories. So it will be 550,000 calories, but in short we say 550 calories. That is the food calorie, capital CAL. Then we can convert it into joules. Small CAL is equal to 4.2 joules, so we will multiply it 4 by 4.2, and that amount of joules of energy is contained in 100 grams of peanuts. So this was energy and its various forms and units. Now, microscopic and macroscopic form of energies. Now a system has many forms of energies, and the sum of all energies for a system is called the total energy. Total energy of a system. So total energy of a system, E, is equal to sum of all forms of energy that a system possesses. For example, it possesses internal energy, it possesses kinetic energy, it possesses potential energy, it possesses electrical energy, it possesses magnetic energy, then there is surface tensile energy, etc. All these forms of energy of a system is called the total energy of the system, denoted by capital E. And we now usually talk about unit mass basis, which is specific energy, which I talked about in the previous videos, that specific energy is total energy per unit mass. So it will be U by m, Ke by m, dividing mass for all, potential energy divided by m, and dot dot dot. So it will be E equal to capital U divided by m, we denote it by small u, then small ke, small pe, etc. So total energy of a system, or specific energy of a system. This is the total energy posed by a system. Now this total energy consists of two parts. One, this part, and another, this part. The internal energy is associated with microscopic activity, microscopic or molecular activities. Molecular activities, which means molecules of a system are in a random motion, constant motion. Molecules translate, they circulate, they rotate, they vibrate. All these microscopic forms, all these molecular forms of energies of a system are called, or the microscopic form of energies, and we call them internal energy of the system. The sum total of all these molecular forms of energies of a system is called the internal energy of that system. And the energy posed due to motion, due to gravitational effects, due to magnetic effects, due to electrical effects, due to surface tensile effects, all these forms of energies are associated with the macroscopic nature of the system, because gravity acts as a whole on the system. So these are all included in the macroscopic forms of energies. Macroscopic form of energies. So this is microscopic energy versus macroscopic energy. Now microscopic energy as a latent and sensible heat. What does it mean? Now we know the molecular activity. Suppose we have a system, there are molecules, they are in random motion. How do we feel that random motion? We feel that random motion in the form of sensible energy. Sensible energy and latent energy. Sensible energy is that portion of heat that we give to a substance and it raises its temperature. That's the sensible energy. And that portion of the heat that we give to a substance which does not raise its temperature but changes its phase, that stays hidden, that amount of energy stays hidden. That's why it's called a latent energy, because latent basically means it has come from the word hidden. It's, I don't know whether Greek or Latin, in Greek or Latin it means hidden. So it's hidden energy, because the amount of energy that we give stays hidden. It is not manifested as change in temperature, increase in temperature, but it changes phase. That it is like when we heat water, until it is not boiling, its temperature continuously raises. So that amount of the amount of heat that gets absorbed by the water until it starts boiling is the sensible heat. And once the water starts boiling, if we put a thermometer inside it, once it starts boiling, the thermometer will keep showing 100 degrees Celsius, and it will not increase. Although we are supplying continuously heat, where is that heat going? That heat is changing its phase. It's making the liquid to become vapor. So that is the latent energy. So these internal form of energies, we sense them in two forms, either sensible energy and latent energy. So that heat that we know, heat or thermal energy, that basically is the manifestation of these microscopic activities, these molecular activities, these microscopic form of energies. If a system has molecules, if there are two systems, one has molecules moving at low speeds, doing low activity, having low kinetic energy at the molecular level, and one has higher another system has molecules that move at higher kinetic energy. The system that has molecules at higher kinetic energy will be hotter, and this will be colder. So higher activity molecular system will be will be hotter, and this will be colder. This is what I mean, that the molecular activity of a system, the molecular motion of a system, is what we sense as heat, whether sensible or latent. And because we know from the kinetic theory of gases that average kinetic energy of molecules, one of the postulates of the kinetic theory of gases is average kinetic energy of molecules is directly proportional to the square root of absolute temperature. That's why higher the kinetic energy of the molecules, it will be hotter. It is proportional to the square root of the absolute temperature. So internal energy is related with heat, in other words sensible heat or latent heat. And the macroscopic form of energies are many: the potential energy, kinetic energy, electrical energy, magnetic energy. Now suppose we have a system in which there are only three forms of energies: internal energy, kinetic energy, and potential energy. Such a system is called a simple compressible system, as I have said this before. Simple compressible system. So system that does not have electrical energy, magnetic energy, surface tensile energy, and other forms of energies. It just have three forms of energies: internal energy, kinetic energy, and potential energy. If it is at rest, we call it simple compressible system. Now, simple compressible system has only three forms of energies. We have to remember these three forms of energies. And when we hear about simple compressible system, we mean it has one microscopic energy, that is internal energy, and it has only two macroscopic energies. If it is at rest, if the system is stationary, if that is, it has kinetic energy and potential energy only. So this is microscopic energy related to latent and sensible. Now internal energy and enthalpy. The difference between the two and what are they? Basically, the true form of energy here is the internal energy, and enthalpy is not basically a true form of energy. It is a true form of energy, but it's not like a specific form of energy, just like internal energy, kinetic energy, potential energy. It's basically a combination property. So we know internal energy is the sum of all microscopic form of energies of a system, which is manifested as heat, which may be latent or which may be sensible. Now there is enthalpy. Enthalpy is basically combination property. It is the name given to the sum of two properties. It is denoted by H, and it is the sum of U plus pressure by density, or U plus P small v. And we know from the last time that reciprocal of density is specific volume. So this is enthalpy. So basically enthalpy is not a true form of energy in itself. It is basically name given to the sum of the two forms of true forms of energy is internal energy, and this is called flow energy or flow work. Flow energy or flow work. What is it? For example, we have a system which consists of, say, liquid, and liquid is at rest. It is a stationary liquid in the container. So what it has is, if it is a simple compressible system, what it has is, it has three forms of energy. It has internal energy, it has kinetic energy, and it has potential energy. That's it. But if it is flowing, it has one additional form of energy, that's called flow energy. Because stationary system and the flowing system has one thing that is different, that's not common between them, is that one flows and one do not flow, and we need energy to make this fluid flow. That flow energy, the energy that pushes the fluid forward to make it to flow, that energy is the flow energy, and that is denoted by PV, or P by rho is the flow energy. So for a stationary liquid in a container, P by rho is 0 because it's not flowing. If a liquid is flowing or air is flowing, P by rho has some value, it's not equal to 0. So simple compressible system means a system if it is stationary, if the system is stationary, simple compressible system is the sum of, is the system which has internal energy, kinetic energy and potential energy. But if the system is flowing, then the flowing simple compressible system has fourth form of energy, which is internal energy, kinetic energy, potential energy and flow energy. Since for a flowing system these two energies are always together, because if a system is flowing, it always has P by rho, and whether a system is stationary or flowing, it always has U, because it is always composed of molecules, and those molecules are always in random motion. So internal energy and the flow energy will always be together. That is why they have been coupled together, P U plus P by rho, and they have been given name H enthalpy. That's where this enthalpy term came from. So for a stationary system, we write total energy as, for a stationary simple compressible system, total energy, internal energy, kinetic energy, potential energy. And for a flowing simple compressible system, total energy is, in place of U we write H plus Ke plus Pe, internal enthalpy plus kinetic energy plus potential energy. So this was internal energy and enthalpy. Now specific heat. Suppose this is a container, it has liquid, or this is any system. We put a thermometer in it and we heat it. Now we give it Q amount of heat and it raises the temperature. Now the amount of heat given to this system, which raises and it has the mass of this is unit mass. It has unit mass, which means say 1 gram, 1 kilogram, 1 pound mass and all that. Suppose we take 1 gram of water or any substance, we heat it, and the amount of heat that is absorbed by the water, so that the temperature of this unit mass of substance changes by 1 degree Celsius. The temperature change occurs by 1 degree Celsius. That amount of heat that we supplied so that this unit mass's temperature changes by 1 degree Celsius is known as specific heat. Now this specific heat can have two values depending upon the system. For example, if this is a closed container and it has air in it or it has any gas in it, if we heat it, if we supply heat to this system, volume is not going to change. All the heat that we supply is going to raise the temperature. This is one form of the system. And another form of the system is whose volume is not fixed. Suppose piston cylinder device, it has some gas and we heat it. When we supply heat to it, all the heat is not going to raise the temperature of the gas, but some part of the energy, some fraction of the energy is going to push the piston outwards so that the volume increases. So here whole heat is going to increase the temperature. Here some heat is going to increase the temperatures. A part of the heat is going to increase the volume, push the piston outwards. So which of the two heats will be larger in raising the temperature by 1 degree Celsius? Of course, this will be larger, because we have to give extra heat to increase. We have to give heat to increase the temperature by 1 degree Celsius as here. But extra heat will be consumed to move the piston outwards. So this will be always greater. Now since here volume is fixed, so we call it QV, and here volume is not fixed but pressure is fixed, we call it QP. And when we measure the specific heat of these kind of systems, we call it CV, specific heat at constant volume. And when we measure the specific heat of these kind of systems, we call it CP, specific heat at constant pressure. Of course, CP will be greater than CV, as I have explained it. How? Because here extra energy will be needed to make 1 degree Celsius rise, because some part of energy will be consumed in pushing the piston outwards. So this is the specific heat. Now relation of internal energy and enthalpy with specific heat. Now CV and CP has relation with U and H. Now first of all, CV has relation with internal energy. How? Differential change in internal energy is equal to CV dt, and this is for stationary systems, and for expanding systems like piston cylinder device, for expanding or contracting systems for stationary like this, and for expanding like this as I showed. Here we use CV, here we use CP. Here this is for the stationary systems, and the change in internal energy is CV dt, and for these kind of systems we have dH is equal to CP dt. Change in enthalpy is CP times differential change in temperature. Now of course we cannot use these for like U2 minus U1 is equal to CV T2 minus T1, because this is the exact value of specific heat, but we know this is the differential change in internal energy. We have to convert this equation into finite change, delta U and delta T terms, and similarly delta H, finite change in delta H in terms of delta change in finite change in temperature. How? We know here U is the function of temperature, and here H is the function of temperature. When temperature changes, U change, temperature changes, H change, and CV also changes with that, and CP also changes with that. So what we do is, suppose we raise temperature from room temperature 20 degrees Celsius to say 100 degrees Celsius. This is our working temperature range for our system. So what we do is we take average temperature, we take average of 20 plus 100, 20 and 100, and which is 60 degrees Celsius. We find the value of CP and CV at 60 degrees Celsius. That is the C average and CP average and CV average, and write the finite change is approximately equal to CV average delta T, and finite change in enthalpy is equal to CP average into delta T. So here we can find U2, we can write U2 minus U1 is equal to CV average value, which will be the one value, T2 minus T1. If we know the initial temperature and the internal energy value, and we know we are raising the temperature from 20 to say 100 degrees Celsius, we know 100, we know 20, we know initial value of internal energy, we can find the final value of internal energy or final value of enthalpy. Now this is for gases though. These equations are applicable for gases. Now we have substance in fluid mechanics that we study, or substances will be either liquid or gas. Now for gas we use ideal gas equations, because mostly we will be dealing with the ideal gases, and we will use these ideal gas equations, P is equal to rho RT, ideal gas equation of state, or these ideal gas equations. And if it is the real gas, we either have alternative forms of ideal gas equations, for example van der Waals equation, or other equations we have that are useful for the real gases, or we use the property tables for these real gases. Mostly the gases in the system will be ideal, so we will be using these kinds of equations. But what about liquids? For liquids, since liquid does not expand or contract like gas, so there is no meaning or separate meaning of CP and CV. That's why for incompressible substances like liquid, CP and CV are same, and we just call it C. So internal energy, for change in internal energy of this incompressible substance, solid or liquid, it will be C average delta T for liquid. C average, not CP average or CV average, because in case of liquids and solids, CP and CV are same. But what about delta P? What about delta H? What about delta H? These two equations are for gases. But what about two equations for liquids in fluid mechanics? For this equation we have this, and what about this? How to find the change in enthalpy of liquid? We cannot use CP because CV and CP are same, that is used for internal energy. So what do we use is We know enthalpy is basically by definition U plus P by rho, and change in enthalpy for liquid will be written as delta U plus delta P divided by rho, because for incompressible substances rho is constant, which is liquids and solids, rho is constant, and delta U is CV average delta T. So C average delta T plus delta P divided by rho. So this will be delta H for liquids, this will be delta U for liquids, this will be delta H for gas, this will be delta U for gases. So this is relation of internal energy and enthalpy with specific heats, and this was the internal energy and enthalpy of incompressible substances. So this was all about today's video. Thank you.